Ladies and gentlemen, welcome to the next session of our tech session. For Q&A, kindly key in your questions at the Q&A chat box. Do visit our virtual exhibition and discover the latest water innovations and technologies. The exhibition will be live for 24 hours during this whole week. Do enjoy the next presentation.
Good morning, everyone. My name is Mohammed Sifon. I'm from Kemsan Consultants in Berhad. And on behalf of Malaysia Water Association, I will be moderating this session. We are in Hall 3, track number 3. And the next presentation will be on the topic of Triton Underdrains, increasing WTP capacity quickly and reliably by John Truman of Acceptance Group Private Limited, Australia. John, the floor is yours.
Thank you, Mohammed. Okay, let me just share my presentation. Okay. Well, hello everyone, salam. Hopefully I pronounced that okay. I thought this would be a good opportunity to give a bit of an overview of Acceptance Group. I recognize that Acceptance Group is a new brand in your market. And while some of the names on the screen might be unfamiliar, you may recognize brands like Johnson Screen and Passivant. So these are some of our brands on the left. And you may know us as Passivant, Nograth, Johnson Screen, Contrashare, Airvac. We are a global company. We've got multiple locations worldwide. Here's a snapshot of our locations worldwide. We're down here in Brisbane, Australia. And as you can see, we have multiple locations worldwide. So this is our factory in Australia. We do in-house manufacturing. There's no external operations. All the laser cutting, folding, fabrication is all done at the site in Geebung, Brisbane, Australia. This is where Triton products would be manufactured if we do deliver this product into Malaysia. We began manufacturing the Triton in Brisbane in 2016. The product has been around since the late 90s though. We have hundreds of installations around the globe in Europe, New Zealand, and the US. But nothing to date in Malaysia as we haven't yet accessed the region. From a technical and installation reference point of view, this is a well-founded product that has been accepted in a lot of jurisdictions that have high water quality standards. Therefore, we see no risk in Malaysia. So here's a video which I'll start and pause a few times. So where a Triton underdrain lives in the process is in a water treatment plant in the filtration stage or in a wastewater treatment plant at tertiary stage. It's the last major treatment step. Upstream of this, you would typically have a water feed from a river or a dam that comes through the pump station that would go into a flash mixing tank dosed with a coagulant. Then from this tank, it goes into a clarifying or pre-sedimentation tank. From there, the sludge is scraped away and sent to the sludge handling process, leaving the top relatively clean. However, there are still fine particulates that you may not see with the eye. So the next step is typically gravity filters or membrane filtration step, which is where we come in. So as you can see, the first layer is the water that comes off the pre-sedimentation tanks. That dirty water then filters down into the layer of media, e.g. sand or carbon. It's just note here that in Asia, we've seen that it's sometimes typical to have a separate media system. So you have a sand media system and then downstream separate carbon system. In Australia, we typically we keep these two media layers together, but we can adapt to the requirements. So the pros of splitting the media up is the depth of media. The deeper the media, the more filtration you will get out of it. E.g., you can run the filter for 2 to 3 times longer than mixed media before requiring backwash. So where do we fit into the process? We fit into the process with the Triton underdrains and the distributor underplates. So the underdrain stops the media from flushing out. It's a 200 micron slot, and the sand that sits on top is 0.6 millimeters. So a rule of thumb is that the media you're trying to retain should be double the size of the media. So that's to ensure a uniform filtration and backwash flow. So if you're familiar with the header lateral system, you consider the channel as the header and the Triton as the lateral. The lateral is collecting all of the flow, and that flow is moving into the center of the Triton and then dropping down into the channel. So the Triton's job is getting a uniform flow across the entire length. So just imagine if you just put a V-wire screen with no flow control, you would get preferential flow just above the channel. So to stop that, we have these little things, which are channel rods. Okay, let's just keep this video playing. Okay, so in the filtration part of the video, we're showing here the distribution of the flow flows through the Triton. It's controlled by flow regulators. The top of the screen is just a standard V-wire, and underneath it is a U-shaped channel rod. And this channel rod has a series of holes in it, and these holes are specific diameter and spacing, and depending on where we need the flow to be distributed across the length, we change the hole spacing and diameter. So it is these channel rods and holes that are regulating the flow, and the V-wire screen is retaining the media. It's a simple concept, but it's very effective. So when we quote for jobs, a typical specification that we guarantee is 95% flow uniformity. So the key to uniformity of filtration is the Triton is to have a uniform filtration and a backwash. which is super important as you want to get the most out of our filter medium. Poor uniformity will give what we call preferential flow in the middles, which means that you don't utilize the media on the left and right. Okay, let me just keep playing this. Okay, so the control of the filtration and backwash cycles. So this part of the video shows it going into backwash mode. You can see the backwash water and air comes in through a separate line and can be pumped into the same channel. Previously, old air systems required a separate airline header coming from the top, and often you couldn't backwash the air and water at the same time. But with our system, you can do it simultaneously. In the backwash phase, there is usually an air phase and a water phase. The point of the air phase is to really agitate the media and breaking up mud ball formations. The filter media can get very muddy. Air bubbles are very good at breaking that up. The next stage or the next phase is air and water, taking the process from the volatile air only phase to a calmer air and water phase, and then the water only phase, which then ramps up the backlog water. See the air valve opening here. It's the air only scour. Air and water, and then we end with the water only. So I hope you enjoyed that video. It's quite neat to see it all in operation. Okay, so this slide shows plenum. If you're pumping air and water into the central channel, you're going to have an air gap at the top and water at the bottom. The slot in the distribution pipe doesn't start at the top, it starts about halfway. And what happens is the air pocket is pushing down into the top of that slot in the pipe, and that air is pushing into these slots while the water is coming in underneath. It's a very effective way of getting an even flow of water and air across each Triton. And once you get an even flow of air and water flowing through the Triton, there is another plenum that forms in the Triton that basically causes the water to come out the side of the Triton and the air on top of the Triton, which is why it's important to have these holes in the channel rods. At the bottom of the channel rods, there are bigger holes where the water comes out, and at the top, there's smaller holes where the air comes out. So the advantages of this type of system, most of it is stated on the slide, but the important points are the life of the this type of system is around 20 to 30 years, with immediate change around every 10 years. Versus, say, for example, a nozzle type system, which usually lasts around 10 years. When you go and visit a site, you can see an old filter. It may have dead zones, which means you're losing filtration capacity. So the Triton filter is very simple to install. They get bolted to a concrete slab, and that's where we get our installation speed. Comparing to casting in a nozzle, plan and floor, you would save considerable time. It would take about a third of the time. The installation for our Triton would be 1 month compared to 3 months for a nozzle type system. It's very important when comparing our stainless steel Triton to, for example, 1,000 plastic nozzles, that this cost would be significantly higher. However, if you consider the final cost, final install cost, we are typically 10% less because you are not mobilized on site for 3 months. You are mobilized on site for only 1 month, so you save on your labor, storage, amenities, etc. Okay, this is a typical nozzle filter. You can see the nozzle is every 30 centimeters here, and you will have these very high localized velocity points, which is why you need to put this gravel layer in. You need the gravel to bring the velocity profile up to a height where they overlap. The gravel's not doing anything, it's just retaining the sand. The sand media is what's doing the work. So with our Triton, you don't need this gravel layer, and it really adds up for a large job. The major benefit is you don't need the gravel, and it can be replaced by the media, so it gives you more filtration capacity. This is great for a refurbishment type job because straight away we can add more filtration capacity because we don't need the gravel layer. These points here are quite important too, around elimination of the cracked nozzles and laterals, plenum floors, and blocked apertures. We've discussed the media quite a bit, but I'll just briefly discuss some different types. So sand is the most common media used for drinking water for a tertiary filtration process. There's constraints that around the sand that it must be around river sand and a silicon content of at least 80%. So this uniformity coefficient basically means it must be nice and round. So it can't be any type of sand. It has some specific requirements around that. Okay, the next type of media that's commonly used is activated carbon. You'll find many potable water plants rely on activated carbon for the removal of dissolved, mainly organic impurities. So we have some specific requirements around the carbon here. Powder activated carbon, particle size 1 to 150, granular 0.5 to 4 millimeters, and we have an extruded activated carbon. So both the powder activated carbon and the granular, they're both widely used. And the last type of media is what we call neutralization media. So they're products that can be used as chemically reacting filter material and open and close fixed bed filters. These are typically used for hardening soft waters or softening hard water. Okay, here is a backwashing video. Okay, so this is a typical commissioning step. We call this a bubble test, where you run the air backwash. You fill it with about a foot of water, and what you want to see is a nice uniform flow. And on this video, we saw this. You saw the air bubbles right across the Tritons. There was a uniform, and if there's a uniform flow, then it is ready to have the media dumped in. If the flow is, if it's not uniform, it means the floor is not level and the Tritons aren't level. The way Tritons are installed is you can jack them up and you can re-level them. The hold down points of the Tritons are threaded, so basically you can just wind the jacking bolts up and down and then check with a level to make sure it's flat. This is really useful for contractors, makes it quite forgiving if the concrete foundation is not level. For a retrofit on old concrete floors, this is an advantage because you don't need to destroy the existing floors. You can adjust the Triton levels to suit. So I'll just play that once more. Okay, now I just want to run through some case studies that demonstrate the Tritons in action. This is a case study for a large project in Naperville, USA. It was presented by the end user, where in summary there was a 50% saving, resulting in a $2 million saving because of the reduction of the total project timeline from 4 years to 2 years. So very, very significant. So the capacity of the filters was improved from 32 megagallons a day to 45. We increased the filtration performance and we allowed more robust operational flexibility. So yeah, the main benefits was the drastically reduced project timeline from 4 years to 2 years, saving $2 million, which is very, very significant. In terms of the filtration rates, it was increased from 120 to 170 megaliters per day. This was the water quality with nozzles compared to the water quality with Tritons. So because of the higher filtration rates, the incoming influent increased from 3.2 milligrams per litre to 7.3 TSS, total suspended solids, yet the average TSS removal increased from 54 to 78%. So these are just showing some old photos here. And then with the Tritons installed here, and you have the original design and the new design. So fairly impressive numbers here. And this site is available for site visits in the United States. So these next couple of slides show our CFD and FEA analysis tools. And these are part of our standard suite of tools we use when preparing tenders and validating our models and our processes. So this shows you the CFD analysis capabilities. We have full in-house, full-time CFD modeling team in the USA. So we check the CFD performance through the Triton itself, and you can see in the top left half a section of a Triton. We also check the central channel for uniformity of flow, and putting it all together, we have all the Tritons in a filter, and we can check the uniformity of flow through the entire filter. So you can see there's a few steps for optimization. FEA modeling capability. So FEA analysis, you do not know that. It demonstrates how strong a product is. So for example, lifting pressures, the strength of anchoring, and a crushing test. This is a differentiator among our competitors and is very useful. Okay, sorry, let me go back a step. So this was a backwash with the media in it. And again, just illustrating the uniformity of the backwash. Okay, so this slide shows the removal of old floating nozzle floor, where we removed it. We put new formwork in and concrete. Then we install our central channel, and the concrete cures for roughly 21 days. So yeah, this slide is really, pretty important here. It's fast and simple. This is a big differentiator with our Triton underdrain system. So this is installing the central distribution pipe, and the guys here are installing the Tritons onto the distributor plates. For this size Triton, they will be done in typically 1 to 2 days. So you have 21 days of curing time plus 1 to 2 days makes for a very quick installation time. Yeah, so just to elaborate on this, so very basic installation with simple tools, basic tradesman skills required. There's no, no advanced level of installation requirements. It can be done by many different types of trades. Okay, so this is just an example of the different types of drawings that customers would receive. So generally it's one drawing of the distributor blade, one drawing of the Triton assembly and how the Tritons go into the filter over the distributor plates. So there's 3 drawings up, very simple process. So that's the first drawing, second drawing, and the third drawing. So this is another installation video. Does have some subtitles in Germany, so I apologize for that. It was made by our distributor in Sweden, all mechanical installation. When you see the backwash section of the video, you can see the muddy water overflows into the launder to the downstream process. So let's play this. So just pause it there. The guys here have welded on some lifting lugs here, but you typically don't need any welding equipment. It's all with basic handheld tools, but this is just to help with installation of the distributor plates. So they're putting the media in now. These are the launders. Video just shows you how simple the entire installation process is. So this is a showcase project for us in Australia with sec water. So at 500 to 850 megalitres per day, it's the second largest water treatment plant in the Southern Hemisphere. The largest is Prospect, which is about 1,500 megalitres. On the right side of the slide here, let me get my pointer. You can see example of the old drawings that illustrate how we can work through complexities in your project. It's not uncommon to have little information to work with us and there to be lots of unknowns. In this case, the filters were very old and we were unable to rely on the drawings. In addition, we had a very short lead time and the project required extensive strength and hydraulic testing, which is why we have such extensive FEA analysis available. So yeah, it's like I said, the capacity 500 to 850 megalitres per day. Yeah, interesting enough, this supplies 70% of Brisbane's water, so very critical asset. It was very important to make sure this job was correct and on time and no issues. The filter dimensions were 7.72 by 12.8 meters. Okay, so some of the challenges were around the short lead time, and that's one of the reasons why we're able to win this job, is because the total commissioning time and installation date, like we're saying, is very quick. So this is the plant here. So there are 20 filter cells. There's 10 on each side. So the central distribution plate was made to order, and so we had some surveyors going here with a laser to accurately and manufacture to suit. So we have that ability as well. So yeah, the nominal peak delivery is around 750 megaliters per day. Like I said, 12.8 by 7.7 meters the filters are. Here's a website link. You can actually read about it online, and this site is available for site visits. So very successful project for us, and these are the types of projects we can do in Malaysia and surrounding areas. So thank you. That was a little bit quicker than I thought. I must have been speaking a bit faster, but I really hope you got some value from that presentation, and goes to show the simplicity installation of the Triton Underdrain system. And yeah, if you have any questions and comments, please let me know.
All right, thank you, John, for the presentation. As you said, you're probably a bit earlier than time, but we have approximately around about 20 minutes of, of time while we are aggregating and queuing the question. Let me introduce yourself for the incremental audience. John's career has spanned more than 15 years of experience, which time he has developed a portfolio of achievements inclusive of people management, business development, channel management, sales, marketing, campaigning, complaints resolution, and project management. He brings to the table a mix of technical and personal skills that allow him to effectively network and identify with both internal and external stakeholders. John holds a Bachelor of Mechanical Engineering from Auckland University of Technology. He has worked in New Zealand, China, Japan, the United States, and now resides in Brisbane, Australia. So that explains the detailed presentation, and it comes together with the technical details, even drawings, John, I must say, because usually that's quite difficult to be shared. Right. First question, queuing, John, may I share with you now that question is, what would be the pressure that required for the water to pass through the sand filter and underdrain? Is the underdrain having any advantage on this compared with the conventional filtration system?
Yeah, so in terms of, so the pressure drop is very, very low through this type of system compared to the conventional type. So very, very minimal pressure drop. So that helps in terms of the designing the hydraulics, and there's very little head loss in terms of design requirements.
How is it compared to the conventional systems? Have you got some background data on it to compare with?
I probably don't have it on hand, but I could definitely, we can definitely supply that afterwards on some one-on-one type basis. But yeah, there's obviously a lot of variables that go into in terms of filtration rates and the backwashing, the capacities. There's lots of variables, so we can calculate that for the consultant or end user if required. So.
Right. That probably come with some site assessment data coming from potential clients or user, right?
Yeah, that's right. So we would need to, yeah, like one of my slides, I said the information can be sometimes very limited. So if possible, we would like to go to site and assess and to gather as much information as we can. If we need to do laser surveying to actually measure the filter bed area. We can do that as well. And sometimes the drawings are available. It's just trying to find those through the right channels.
Yeah. Do you have any references in Malaysia, John? I mean, looking at all the examples that you have posted in your presentation.
Yeah, we don't. That's because we really haven't accessed Malaysia yet. We have thousands of installations worldwide, the US and Europe, but it's really that we haven't focused on Malaysia. So we have recently engaged with a company called Arakan in Malaysia, and so we're looking to work with them very closely, and yeah, hopefully get some references in the upcoming years.
Yeah, certainly. So with all these installations that you have in Australia, in Europe, what is the typical life of a Triton installation then, with all the experiences that you have?
Yeah, like it's a good question. There can be many factors, but typically we find around the 30 years mark. In some cases, there has been even longer life than 30 years. So it's an asset that is very has a long life tenure, and you know, there's very little moving parts. It's very mechanical, you know, basic media. So yeah, it's a fairly extensive tenure of 30 years roughly.
Well, that's quite extensive actually. So with this duration, how often does the media need to be changed in? I mean, knowing that you've mentioned about this extensive years of operation.
Yeah, it's a good question. So it's typically in the order of, you know, roughly around 10 years you would look to replace the media. So when I first started getting involved in the Triton system, learning about it, I was actually quite surprised about this, that it was every 10 years. I would have thought it would have been more frequently, but going through all the case studies and talking to our field service engineers, our project managers, consultants, users, it's generally around that 10-year mark, which is yeah. So very little to do for the plant operators. You know, if it's designed with the analysis up front, the CFD, FEA analysis, and you have a nice uniform filtration flow and backwash, there's really very little that can actually go wrong. So very user friendly for the operators, and yeah, around about a 10-year changeover time for the media.
All right. There's a queuing question now, probably a bit burning question, because talking about what supply cost per square meter, based on your experience in installing those in Australia, in Europe, and other areas.
Yeah, look, it's a good, very very important very important question. So if we were comparing this to, for example, a nozzle type system, filtration system, and for example, if you had 1,000 nozzles, it would be, you know, it would be very, our system would be very expensive upfront, the initial asset capital upfront cost. So, but the trick is to look at the complete life cycle of the project. Look at all of the installation costs. For, like I was saying, it's you know, roughly a third of the installation cost. You know, as I mentioned earlier in the presentation, 1 month compared to like a 3-month installation time. So you don't need the project engineers, the commissioning engineers, the infrastructure of the amenities, that sort of thing. So when you consider the life cycle, installation life cycle of the project, we generally would come in around 10 to 15% less than a conventional type nozzle system. Yeah, for exact cost, we'd be happy to look at specific inquiries with our agent Arakan. So yeah, it can be a hard sell up front if you're just looking at the upfront capital costs, but it's just about education and making sure people understand the complete timeline of the project. So I guess that's my job as a salesperson, educated to do. So yeah, hopefully that answers your question.
Yeah. There's one coming. Sorry, the quick question here is based on the presentations. What is the difference between PVC and steel underdrains? Because I think it was presented in your presentation, right, on the materials.
Yeah. So our stainless steel is our standard type material we use, 316 stainless steel. So PVC can be used in the underdrain, but it's typically used in like a seawater application. So we are looking at designing PVC. We're looking at some new design for our PVC in terms of enhancing the mechanical strength and improvements around that. But generally, at this stage, we only offer stainless steel for freshwater type applications. So yeah.
Would there be a performance difference? I suppose not, but in your experience of your installation?
Can't see there being a performance in terms of filtration rates. I think just in terms of mechanical strength, I think anything with plastic can potentially prematurely sort of fail. That's what happens in a plastic nozzle type system, that they can fail early, and that reduces the life of that type of system. So yeah, I think we're working on lots of there's lots of technology. We're doing lots of R&D in the background in terms of plastics and different materials as well. We have a fairly extensive research and development team. We look at prototyping different materials, but at this stage, we're fairly comfortable with stainless steel option.
Yeah, that's quite interesting, because that brings us to the next quick question: is what will be the gasket materials adopted or used in this installation of this Triton?
Yeah, that's a good question. So we typically use like a silicon or EPDM gasket material that's been, that's accepted in most regions globally as the two predominant elastomers. So if there is a certain requirement for a different elastomer material, we can definitely discuss that. But typically, from our experience, it's those two materials are generally the most common type.
Yeah, I guess it depends on the type of water to be processed, isn't it? That would be subject to the analysis earlier mentioned.
Yes, that's correct. Yeah, that's right. So if there's some turbidity, or there's some other issues there that we want to look at some different type of elastomer, yeah, for sure we can discuss that on a case-by-case basis. But generally, yeah, we go with thousands of references worldwide. That's typically what's been used in most applications. So yeah.
Awesome. So we have no questions at the moment from the floor, John.
Okay.
So I suppose questions further that are coming in will be forwarded through the organizer, and they will be forwarded to you.
Yes.
Do you have any last probably words for the Tritons, recommendations, or before we?
Yeah. No, thank you, Mo. It's yeah. So we're very proud to be an Australian-made product and with in-house manufacturing. Yeah, we're really looking to grow into the Southeast Asia market through our agent Erican. I think it's, in summary, it's just a very basic, it's simple to install type of gravity filtration, and I think just the simplicity of it, and in terms of maintenance for the operators, it just works. So I just want to say thank you for the opportunity to speak today. I've really enjoyed my time, and please feel free to forward through any questions afterwards. I'd be happy to discuss further. So 100%.
Thank you, John. At the end of this session, we're now concluding it for track 3 of your Triton Underdrains. And ladies and gentlemen, we are now concluding this session. Any other questions can maybe forward to the organizer. Thank you.